Assalamu alaikum, dear students. Welcome to the 11th program in operating system program series, and today we plan to discuss input-output systems. The significance and importance of input-output systems cannot be overstated. What if we don't have hard disk, we don't have monitor, or we don't have printers? Input-output systems or input-output devices constitute an integral part of any computing facility or any computing system. And you'll recall we did discuss briefly the input-output devices and input-output systems while we had an introduction of operating systems, and we also briefly discussed input-output systems while we discussed file systems, and we discussed block special files and character special files which are used to model the input-output devices. And today we plan to expand on our previous knowledge of input-output devices, and today we plan to cover principle of I/O hardware, disks, clocks, character-oriented terminals, graphic user interfaces. We'll briefly discuss principles of I/O software, I/O software layers, and input-output performance issues. You will recall that while we introduced the subject of operating systems, and we learned that one of the most important function of the operating system is to manage the I/O devices. And in managing the I/O devices, primarily operating system helps us, the user, to get out of or get rid of the complexities of the I/O devices. We plainly and simply see the I/O devices and use them without getting into the technical details of how the I/O devices actually function. The operating systems, as we discussed previously, provides us the following I/O related services. The operating system handles the message passing to and from the system. It handles interrupts and errors, and it offers simplifies the interface of the I/O devices with the users, and it offers device independence to some degree. Dear students, there are a number of ways the I/O devices are classified, but primarily the classification stands as block devices and character devices. Now let's look at briefly what classifications are. As I mentioned, character stream devices or block devices, sequential or random access devices, shareable or dedicated devices, write-only, read-only, read-write devices. You'll recall the block devices transfer blocks of data, for example, disk devices. And we previously also learned that the disk devices are represented by block special files in the operating systems. And the commands we use to manage the devices are read, write, seek, if the device is a random access device. In the character devices, transfer byte by byte, as we learned the keyboard is a character device. And the commands which we use for character devices are get, put, one character at a time. Although these devices provide us one character at a time, we can build certain libraries on top of the character devices, and as such we can manage maybe one line at a time for the buffering and for storage or read-write purposes. These are the two main classes of I/O devices: character special devices and block devices. But there are certain special devices which do not fall in the category of either of the character devices or on the block devices. And these devices are, for example, clocks. Clocks do not fall in either in character devices or in block devices. What they do is cause interrupts. And there are certain other, for example, memory mapped screens. Clocks and memory mapped screens, they do not fit in the categorization or classification of block devices or character devices class. Another classification of the I/O devices can be based on their use. For example, we have storage devices. Disks, tapes come in this category. We can classify as transmission devices. Network cards and modems fall in this category. User interface devices, screens, keyboards, mouse, they fall in the user interface devices category. And specialized devices like joysticks, clocks also fall in specialized devices based on their use. Devices communicate with computer system by sending a signal over the cable, or if the device is a wireless device, then it will communicate through the air, or the device will communicate with the system with the help of a cable, and cable can be a bus, or cable can be another communication cable. We'll look at that shortly. Yet we have another classification of I/O devices, the man-readable devices or the machine-readable devices. The man-readable devices, for example, are the printers, graphical terminals, screens, keyboards, mouse, and pointing devices, whereas the machine-readable devices are disks, tapes, sensors, controllers, actuators, and so on. One of the key qualification of the I/O devices is with the speed with which we can transfer, or with the speed with which the I/O devices handle the data. And they are from a few bytes to few kilobytes, megabytes, and even to a few GBs. The devices range from few bytes to the gigabyte in terms of their capability and in terms of their capacity to handle data. Let's look at briefly at the list. For example, keyboard handles the data rate is 10 bytes per second. Mouse can handle 100 bytes per second. 56K modem can handle up to 7 kilobyte per second. Telephone channel 8 kilobyte per second. Dual ISDN line 16 kilobyte per second. Laser printer 100 KB. Classical Ethernet 1.25 MB. Digital camcorder 4 MB per second. ISA bus, for example, 16.7 MB per second. And we go PCI bus can go up to 528 MB per second, whereas Sun graphic adapter, it can handle up to 20 GB per second. As such, we can very safely say that the data transfer rate of I/O devices has a very wide variation, and based on the need, from a few bytes to gigabytes of the information could be transferred per second in these or by these I/O devices. As I mentioned, there are three ways we can approach the I/O systems. The first one is the programmed I/O, which has and provides continuous attention to the processor is required if our I/O is primarily programmed and program driven. Or we can have interrupt driven I/O. The processor launches I/O and it continues until it is interrupted, and these interrupts are generated by clocks, as we will see shortly. Or we can look at the I/O devices from the point of view they access the memory. Direct memory access devices, the DMA module governs the exchange of data between I/O unit and the main memory. Dear students, now we come to a point where we look at the composition of I/O devices. Primarily, I/O devices are composed of two components. The first component is electronic component, and the second component is a mechanical component. And electronic component of an I/O device is primarily the controller. It may be a disk controller, it may be a printer controller, it may be a bus controller, and so on. Controller is a collection of electronics circuitry that can operate a port, a bus, or an I/O devices. I'm sure you are familiar with the serial port controller, which is a simple device to attach the which is a simple device which handle the serial I/O devices and which are attached to the serial port of the machine. Or we can have a SCSI bus controller, which also contains a processor, microcode, and it has its own memory, and it processes SCSI protocol messages. And we can have disk controllers which implement the disk side of the protocol that does, for example, bad error mapping, prefetching, buffering, caching, and the kind of and the other processes related to the disks. Other important issue is how the I/O devices communicate with the system. The I/O devices communicate with the system with the help of a bus or with the help of a port. If the device is external, then the device will be connected to the system with the help of a port. And all the internal component of the system, for example, memory or the disks, if it is internal, are connected to each other with the help of a bus. As I mentioned, external I/O devices communicate with the machine via a connection point which is called a port, and a port can be a serial port or it can be a parallel port. And the devices within the computer are connected with the help of a bus. And what's a bus? A bus is a common set of wires and a rigidly defined protocol that specifies a set of messages that can be sent on the wires from one element of the system to the other element, or from one I/O device to the other I/O device. That moves us to another important concept in the input-output systems, and that is the memory mapped I/O. Each controller in the system has some registers on it, which are used to communicate with the CPU. And these registers primarily are used to communicate with the CPU, and most of the time or sometime these registers become a part of the memory address space. And if they are if they constitute a part of the memory address space, then we call this concept the memory mapped I/O. How it works, let's look at that. As I mentioned, each controller has few registers that are used for communicating with the CPU. And on some computers, these registers are part of the regular memory address space. And this scheme is called memory mapped I/O. In this diagram, we see here in this first part the separate I/O and memory space. This is the memory space, and this is the separate I/O address space. And in the second one, we see the I/O address space is a part of the memory space, and we call that memory mapped I/O. Yet in this the third component of this diagram, we see a hybrid approach. The I/O address space is a part of the memory address space, as well as it has a separate address space. We also have a single bus architecture or a double bus architecture for a memory mapped I/O. Let's look at the diagram. In this first diagram, we see a single bus architecture. We have a CPU here, we have a memory, and we have I/O, and all these CPU, memory, and I/O are connected with a single bus. And all addresses, memory, and I/O go here to the CPU. The I/O address, memory address, the I/O address, or whatever is on this bus, they go to the CPU through this single bus, and we call this a single bus architecture. Whereas here in this second diagram, we see a direct connection between CPU and memory, and here CPU reads and writes the memory over a high bandwidth bus, over this bus, and I/O devices communicate with the memory through this point here. It means we have a double bus memory architecture, one between CPU and the memory, and the other between which connects the memory as well as I/O devices, and at this point the memory port to allow the devices to access the memory. I/O devices access the memory here, whereas the CPU directly communicates and reads and writes in the memory directly over this high bandwidth bus, and we call this a dual architecture or dual bus memory architecture. I alluded to the concept of direct memory access. If we don't have a direct memory access to the CPU, then our performance is low, and in order to achieve the performance, the concept of direct memory access has been introduced. In case if there is no direct memory access, the controller will request the information to the disk, and the information will be read from the disk and stored in a buffer. And whenever CPU needs the information in different iterations, the CPU will read part of the information. At each iteration, part of the information will be read by the CPU, and not all the information can be read. This provides us, this introduce some inefficiency in it. Whereas if we have a direct memory access, then direct memory access card or DMA controller provides us the efficiency, and our CPU operates and functions more effectively than otherwise. How it works, let's look at with the help of a diagram. CPU gives two pieces of the information, or programs the DMA controller with two pieces of information. One is which blocks from the disk to read, and second is where in the memory address space to place that. And then once the CPU has informed the DMA what it needs, where it needs to be, where the information needs to be placed, DMA requests the transfer to the memory. When DMA request comes here, the disk controller reads the information from the disk, and then the data is transferred to the address space in the main memory. And whenever once it's read, then disk controller sends the acknowledgement to the DMA controller. And obviously when the interrupts occurs, when the acknowledgement is received, the DMA controller interrupts the CPU that the requested information has been placed in the memory, and interrupt when it is done. Okay. This certainly, and whenever now once the information is in the main memory and interrupt has been given to the CPU, now CPU goes and in one chunk gets the information which is already available in the main memory and processes whatever process is required. As such, it provides us the DMA, direct memory access, provide us the efficiency of utilizing the information by the CPU. There are primarily three implementation schemes of DMA in the system, and how they are. For example, DMA shares the bus with I/O units. We see this bus, CPU is on the same bus, DMA is on the same bus, I/O1, I/O2, memory, all are on the same bus. They share the same bus, and performance and simplicity in I/O module. The second implementation, DMA implementation scheme, is that DMA shares the bus only with other DMA or with the CPU or with the memory. As we see in this diagram, this bus, we have a CPU connected, we have a DMA connected, and we have a memory connected. No I/O device is directly connected with this bus. However, we have the I/Os directly connected to the DMA, we may have another DMA connected to with this bus, but no IO can be directly connected with this bus. The third DMA implementation scheme is that DMA has its separate bus, and the schematics is shown here in this diagram. We see CPU and DMA and memory share the bus, and DMA has its own bus, and IO devices are connected with this through this bus with the DMA. Dear students, we have been consistently and continuously discussing the reads, writes, and random access and disks. I'm sure now is the time to look at the disks in a little more details, and let's do that. This is the physical hardware or the disk geometry, where we have this is the ARM, and these are the read-write heads. We see here we call this an ARM, and these are the read-write heads, and these disks, they rotate in this counterclockwise direction. We have tracks here, as we see, which actually contain the data, contain the information, and the cylinders are subdivided into sectors. As we see, from this point to this point is one sector, and then we have from this point to this point we have a sector, from this to this we have a sector, and so on. But the actually surface on which we store the information is called the track, and these disks revolve with a very high speed, and since they are mounted on this spindle, and these disks revolve, and wherever the information is, if the information is here and we want to read it, this disk will revolve under the head, read-write head, so that we are able to read the information from the disk. The performance of the disk is a function of three things, and these three things are: the seek time is one element which has influence on the performance of the or the speed with which we can read the information. And the second element is the latency time. A latency time is, let's say, from here, if we want to read the information from this track, this will have to move this way, and we call this latency time. And then is actually the transmission time. These are the three elements which are influential in how easily and with how much speed we can access the information on the disk. And there are certain performance parameters for the disk, and these performance parameters constitute that how much information we can store on the disk and with what speed we can retrieve that information whenever it's needed. Let's look at that. We see sector. We have seen physically how the sector is located and denominated by k bytes, and its size ranges from 32 to 4096 bytes. Then we looked at physically where the track is, and it is represented by S sectors, and the size ranges from 4 to 32 sectors. Then we looked at the cylinder, which is represented by T tracks, and size is from 4 to 32 tracks. Then surface J tracks. I mean, for each disk we have a surface, upper surface and a lower surface, and the size is from 75 to 500 tracks. And the volume V is represented by V, and the size ranges from 75 to 500 cylinders of 4 to 32 surfaces. And if we want to calculate the total storage, it will be K into S into T into G. And how we get to the block address is equal to sector plus S into surface plus cylinder into T, and this thing is in brackets. I would like to show you a comparison of a primitive kind of floppy disk and a high-speed disk drive of Western Digital. I'll show you the comparison of these two. We see here various disk parameters, and here IBM 360 KB floppy disk and Western Digital 8300 hard disk. A number of cylinders we see here 40, and here we see 10,601. Tracks per cylinder 2, 12. Sectors per track 9, 281. Sectors per discs 720, and here it is 35 million, 35.742 million. Bytes per sector, both the same, 512, 512. Disk capacity 360 KB to compared with 18.3 GB. The seek time for adjacent cylinders, and here we see the seek time in average case 75 milliseconds, 77 milliseconds, and here it is 6.9 milliseconds. A rotation time we see here 200 milliseconds, and in case of WD hard disk it is 8.33 milliseconds. The motor stop start time 250 milliseconds compared with 20 milliseconds of a hard disk. Time to transfer one sector, here we have 22 milliseconds, here we have 17 mu seconds. Latest hard disk provides us much more storage space, as well as much more speed with which we can access that information for our processing purposes.